Alright, this video is going to cover Unit 8, which is States of Matter and Thermochemistry. Alright, to start with, let's do a quick review of the states of matter. A lot of this stuff is more concepts this unit than math. What math there is going to be pretty basic. So, solid, liquid, and gas, I feel like I shouldn't have to go too much into this because it's something that you've learned since pretty much elementary school. A solid's going to have a defined shape. It's going to have low energy, slow particle movement. A liquid's going to be basically your medium size energy level, particle movement. It has a shape, but it's not rigid, so it will take the shape of its container and it will flow. A gas is the most energetic. It has the most movement, and it's going to fill the entire volume of the container. All right. Kinetic molecular theory basically describes what I was saying in terms of the particle movement. Essentially, everything's made of particles, and that the kinetic energy is proportional to the temperature. Solids have the least amount of energy, gases have the most, and the motion that the particles have is going to be caused by the amount of energy. Therefore, low particle movement in solids, but high in gases. For gases, pressure's created by the particles bouncing off the walls of the container. The more movement, the higher the pressure. Gases are so far apart, there are no attractive forces between them. However, solids and liquids do have attractive forces, and this is what keeps them close together. Alright, the attractive forces, we have basically two types. We have intramolecular, which is within a bond, and this here, again, that we talked about this in class, that's going to be your covalent and your ionic bonds. And then intermolecular is between molecules. So we have three types. Dispersion, remember that these are the weakest of the three, and that it occurs in everything. And it's going to basically be a momentarily shift of all the electrons to one side of the cloud. So I think in class the example I gave is, okay, I can't draw a car, but imagine that this is a car and you turn sharply to one side because of, forces and everything like that. Everybody moves to the opposite direction of the car. So then if this was an electron, this would be negative, this would be positive. So we get basically a shift in the electrons, so we get a creation of a temporary dipole. Alright, again, this is temporary. It happens it happens instantaneous. It's temporary, and everything has it. A dipole-dipole, this is where we go back to our favorite word we learned last semester, electronegativity. If I can spell it correctly, let's see. Okay. Basically, as I try to write this, electronegativity is where you have a difference in the electrons. Okay, so let's say hydrogen is less electronegative than oxygen. The oxygens here are going to hog the electrons more. So you're going to have a slight negative on this, a slight positive on that, and we create a dipole here, and these are going to be on polar molecules. Okay, hydrogen bonds is a type of dipole-dipole, except for it only occurs between fluorine, oxygen, and nitrogen, and hydrogen. So hydrogen has to be connected to fluorine, oxygen, or nitrogen. Water is a perfect example of this. These are the strongest. So what's going to happen is you have two water molecules. Again, even though this is bond, this is not a bond. These are all attractions. So these little dashed lines here that I drew, the dotted lines, that's your hydrogen bond. It's the attraction between the hydrogens. Actually, that is incorrect. It would be between the hydrogen and the oxygen. I apologize about that. So if this is attached to another water, this right here is your hydrogen bond. Again, it's not a bond, it's an attraction, but it's between the oxygen and the hydrogen. Alright, like I said before, dispersion is your weakest, dipole-dipole is your middle, and then hydrogen bond your strongest. And this takes this plays into the properties that certain or properties of certain compounds, such as boiling point, freezing point, things like that. The stronger the attraction, the harder and more energy it takes to break. All right, phase changes and phase diagrams. I'm not going to go through all of the phase changes. We've talked about these before. Melting and freezing are opposite. Vaporization and condensation are opposite, and sublimation and deposition are opposite. One thing I do want to mention with this, and we talked about it briefly with heat, is that to know whether these are endothermic or exothermic. So melting is going to release heat, or actually is going to require heat, so it's going to be endothermic. Melting is going to release heat, it is exothermic. Vaporization is endothermic, condensation is exothermic, sublimation is endothermic, and deposition is exothermic. The way I know this is because if we're having to speed up the particles, so let's take melting for example. If we're going from solid to liquid, the energy here increases. Therefore, the energy for the particles increases. Therefore, you're going to need to put energy in. However, if you have solid to a liquid to a solid, the energy is going to decrease. It's going to get smaller. So you've got to release that energy. And that's going to be an exothermic reaction. Now, the point at which something melts is known as the melting point. Freezing point is that same point, except for in the opposite direction. And then boiling point is where it goes from a liquid to a gas. And all of these can be shown on a phase diagram. So a phase diagram is essentially just a graph of the temperature plotted on the x-axis here. So this is the x, your y-axis is your pressure, and you're going to have different lines showing the different phases. So you've got solid, liquid, and gas. The red line here, this is going to be your melting / freezing line. The blue line here is going to be your evaporation, whatever you want to call it, and condensation line. And the yellow line here is your sublimation and your deposition line. Right here in the center, where all three of them meet, that is your triple point. It's supposed to be a T there. All right. Again, so that's your triple point. In terms of looking at these, you're going to need to be able to identify where the phases are, what the different phase changes are, and know how to read it. So if I give you a pressure and temperature, make sure that you know how to go from, figure out what state of matter it is, what phase change would be occurring, things like that. So let me give you an example real quick. So let's say we started here, and we're going to go down to here. Alrighty? So, if we're changing from point A to point B, it would be a sublimation because we're going across this line right here. That's what I mean by know what phase change is occurring. Alright? Okay, so that basically sums up all of the states of matter. Now we're going to talk more specifically about gases, and this is where a lot of the math comes in. Alright, so to start with, pressure is a big part of gases. And pressure, like I mentioned before, is created when you have the particles of a gas colliding with the sides of its container. The technical definition here is the force per unit area, and we have 5 different units of units for pressure. We have atmospheres, kilopascals, millimeters of mercury, torr, and bar. Now, this right here, this relationship here, is something that you need to know. Like, you need to write it down on your cheat sheet. You need to write it somewhere where you can reference it. A lot of y'all, when we had quizzes and stuff, didn't write this down. So the way to read this is that 1 atmosphere, for example, equals 760 millimeters of mercury. Another way to read it is that 101.3 kilopascals equals 1.01 bar. They're all equal to one another, and we can use those, we can use those to convert between different types. All right, so here's an example. The pressure in Denver, Colorado usually is 84 kilopascals. What is that pressure in atmospheres? All right, so we start with this is a simple unit conversion. We start with 84 kilopascals. We want our kilopascals to cancel, so we're going to put our kilopascals on the bottom. Well, if we look at the relationship up there, we see that 1 atmosphere equals 101.3 kPa. That's right here. So we're going to put kPa on the bottom, which is 101.3. We're going to put 1 atmosphere on top, because that's what we want. And then we're going to divide the two. And we end up with an answer of 0.83. Again, a very simple unit conversion as long as you know those units. So again, make sure you write those down. All right. The first gas law really to get into is Dalton's law of partial pressure. Essentially what this is saying is, let's say we have a box and we have a bunch of gases in there. The total pressure of this box is going to be equal to, okay, it's basically going to be equal to the pressure of one thing plus the pressure of another thing plus the pressure of a third thing. If we have a fourth gas in there, all of these pressures together, so we add these up, that would equal the total pressure here. Okay? So it gives you pressure 1 and pressure 2, but you can have as many pressures as you need. So it's a sum of all the pressures equals the total. So let's look at this example real quick. A gas mixture of oxygen, carbon dioxide, and nitrogen has a total pressure of 0.97 atmospheres. What is the partial pressure of oxygen if the partial pressure of CO2 is 0.7 atmospheres and the partial pressure of nitrogen is 0.12 atmospheres? All right, so we take this equation we have, and we take our total pressure right here. We set it equal to X, which is what we're solving for, the partial pressure of nitrogen here, plus the partial pressure of, this is nitrogen, this here is actually CO2. We have what we're looking for of oxygen, we have CO2, and we have nitrogen. So we're going to add nitrogen and CO2 together, which gives you 0.82, and we're going to subtract it from the 0.97. When we do that, you get a partial pressure for oxygen of 0.15. So we know 2 out of the 3, we add them together, we subtract from the total. Very, very basic idea, not too difficult. All right, now let's get into the dead white guys and what they said. All right, first of all, Boyle's law. Boyle's related pressure and volume. All right, so his said P1V1 equals P2V2. What this means, and this is important for you to understand, is that as pressure increases, volume decreases. So make sure that you understand what this equation means. If they're on the same side like this, when one goes up, the other one must go down based on the mathematical relationship here. So again, pressure, this relates pressure and volume, and it says that when one goes up, the other goes down. All right, so let's do a quick example of how to use this. A sample of helium gas in a balloon is compressed from 4 liters to 2.5 liters. If the pressure in the 4-liter container is 210 kilopascals, what is the pressure once it's decreased? All right, so we take our equation up here, and in this instant, instead of trying to rearrange the equations for what we're solving for, which I was doing in class, what I've done here is I've just gone ahead and plugged it in. It seemed like this clicked with a lot more of y'all. So we're going to plug in our P1 here. We're going to plug in our V1, okay? We don't know P2, that's what we're solving for, and we plug in our V2. Now, again, like with other equations we've had, the volume here and the pressure here are a pair. These two go together. So the 4 liters and the 210 kilopascal. Our other pair here is 2.5 and something else. It doesn't matter if one is 1 and the other is 2 or vice versa, as long as these two pairs stay together, okay? Typically what you're looking for is going to be the second one. So I plugged everything in. To solve this, we divide both sides by 2.5, okay? So that means that you have 210 times 4 divided by 2.5, and that ends up being 336 kilopascals. So in this case, these are just real simple plug and chug. The problem is identifying what things are what. Now remember, we talked about all the different pressure units on the previous slide. Volume is going to be in milliliters or liters. So if you see liters or milliliters, that's going to be your volume. All right? Moving on to the next dead white guy. Charles. Charles is going to relate volume and temperature. All right? Now, in a lot of textbooks and stuff, you will see fractions done. Typically it's shown as V1 over T1. Okay? What I've done here is I've condensed it down. So this I think is easier to manipulate what I've given you, but you have to remember they're opposites. So V1 T2 equals V2 T1. Because of that, as volume increases, temperature will also increase. All right? So if this one goes up, this one will go up. All right? With this and with all gases, temperature has to be in Kelvin. You just add 273 to whatever your Celsius is. Alrighty? So again, just to make sure, temperature is going to be in Kelvin or in degrees Celsius, but it has to be in Kelvin when you do your calculations. Alright, so let's look at our example here. What is the volume of air in a balloon that occupies 0.62 liters at 25 degrees Celsius if the temperature is lower to 0 degrees Celsius? So here we go. We got V1, they gave us T2, so this is our T2 here. This is V1 and this is T1. Okay, so I just went ahead and added 273 in the equation here. You can do it separately. We don't know our V2, and we put T1 on the right side of the equation. Again, we're solving for x here, so we're going to divide both sides by 25 plus 273, which is actually 298. So we have 0.62 times 273 divided by 298, and that gives you about 0.6 liters, 0.57 liters. All right. Third gas law, Gay-Lussac's. This one relates pressure and temperature. This is almost identical to volume and temperature. Again, it's opposites. Pressure, or P1 T2 equals P2. This should be T1. I apologize. All right. So as pressure goes up, temperature also goes up. So again, this one goes up, that one goes up. Temperature has to be in Kelvin again. All right. All right. Example. Gas in a sealed container has a pressure of 125 kilopascals. So we're going to make that P1 at a temperature of 30 degrees Celsius. This is T1. If the pressure is increased to 201 kilopascals, this is going to be P2. What is the new temperature? So this is T2. All right. So in this case, we have our P1, which is 125. We're looking for T2. P2 is 201. T1 is 30 plus 273. All right. In this case, our division's a little bit different. We're going to take 201 times 303, which is the sum of the 30 plus 273, and we're going to divide by 125 because that's on the side with x. And when we do that, we get 487 kilopascals. All right. Fourth gas law. Actually, technically fifth if you want to include Dalton's, but the combined gas law combines Boyle's, Charles, and Gay-Lussac's. I'm not going to spend too much time on this because I've just gone through the other three. Again, P1, V1, T2 equals P2, V2, T1. Alright, let's look at an example. An unopened cold bottle of soda contains 46 milliliters of gas confined at a pressure of 1.3 atmospheres at 5 degrees Celsius. If the bottle is dropped into a lake whose pressure is 1.52 atmospheres at 2.09 degrees Celsius, what is the new volume? One thing I want to mention real quick, I said that temperature had to be in Kelvin. For volume and pressure, all they need are the same units. So as long as they're in milliliters, liters, it doesn't matter what the for the units are for these two, except for as long as they're the same in both numbers. All right, so this is our V1 here with 46. P1 is 1.3 and T1 is 5. Okay, instead of being doubles this time or a pair, you're going to have triplets. All right, so P2 is the 1.52. T2 is the 2.09, and we're looking for V2 here. All right, so if we take this equation, we're going to have the 1.3 times 46 times 2.09 plus 273. We're going to set that equal to 152, 1.52, excuse me, times x times 5 plus 273. So we're going to multiply that top on the left, and we're going to divide by what's on the right. And we do that, you get about 39 milliliters. Okay? Again, we're just utilizing the formulas here and plugging in the variables. I think the trickiest part with these gas laws, Boyle's, Charles, and Gay-Lussac's, along with the combined, is knowing which variables go with what. But just as you read, as I was doing, if you just identify, you know, P1, V1, whatever, then you should be okay. Alright, ideal gas law is a little bit different. Okay? It basically says that we're going to now relate the pressure, volume, and temperature to the amount of substance thereof. Okay, so here we go. We've got P times V equals nRT. All right, P and V are kind of obvious. That's pressure and temperature. Remember here, and this is tricky for people, that N is the number of moles. Why is it N? I have no clue. That's just what the letter they chose to do. R is your gas constant. Okay, and T is temperature. Again, T does have to be in Kelvin. All right, we actually have 3 gas constants. All right, that's here. Again, these are going to be, you don't have to memorize these, you just need to write these down somewhere. Alrighty, so, and the difference here is that you're going to have 3 different ones based on the pressure. So whatever pressure unit you have, you choose the appropriate one. Now, if the question does ask for pressure, it does not matter which one you give, okay? Because unless, like in a multiple choice question, if it gives you a particular type of units, like if the choices are in atmospheres, you know to use that. But if it's a free response, then it doesn't really matter which atmosphere or which pressure you use unless it's specified. Excuse me. All right. Now, using the ideal gas law, we talked about in class how you could rearrange stuff, and you could actually associate the molar mass, which in this case is abbreviated MW, to the other components like pressure and volume. And to do that, it's the molar mass equals the mass here, okay? This little m is mass times R, which is the gas constant, times temperature, divided by pressure times volume. We can also relate density to the other variables. So density equals the molar mass times the pressure divided by the constant times, or gas constant times temperature. Alright, so let's look at a quick example here. So that's kind of an overview of those, of the different variables that you can use with the ideal gas law. Alright, an example says, determine the temperature required for 0.014 moles of gas to fill a balloon to 1.2 liters under 0.988 atmospheres. Alright, so this is moles, so it's going to be our N. This is volume because it's in liters, and our pressure is in atmospheres. Okay, so that means that if we go back up here to the top, we're going to use this first gas constant. So, like before, we just plug in what we have. So P times V equals N R, and we're looking for T here. Okay, so that's what we're looking for here. We're going to take the 0.988 and multiply by 1.2, and we're going to divide that by 0.014 times 0.0821. Alright, so our units all here will cancel. And not that doesn't cancel. Alright, and then we're left with an answer of 1,031 Kelvin. So with this one, as long as you can identify the variables, know how to pick the right gas constant, look at your atmosphere, or look at your units. So again, in this case, it's atmosphere, so we use that first gas constant. As long as you can pick those out, you should be good with this type of question. All right. Now let's look at some of the other characteristics of gases. Along the same lines of ideal gas, when scientists were studying, more particularly when Avogadro was studying gases and came up with his Avogadro number, he noticed that if you had equal volumes of gases at the same pressure and temperature, you would have the same number of particles. And what scientists decided to do was they just said, okay, let's set a standard. Let's take this pressure and temperature, and we're going to set it as a standard. So this became known as STP, standard temperature pressure, and the values that were associated with it was 273 Kelvin, or 0 degrees Celsius, and 1 atmosphere. So, though that's the temperature and pressure. Well, along the same lines, we've been talking about temperature, pressure. We've also been talking about volume. And if you look at the calculations, or if you even look at the situation, at this pressure and temperature, if we have 1 mole of substance, you're going to have a volume of 100, or excuse me, not 100, of 22.4. Okay, and this became known as the molar volume. All right. And so what we have here is we now have a new conversion factor, or a new thing we can use to convert between units. So we now know that 1 mole equals 22.4 liters at STP. That's important. If it's not STP, this does not work. But if it's at STP, we can use this relationship to convert between the volume and the number of particles, or excuse me, the number of substance, the moles. All right. So, in this case, let's look at our example. Calculate the volume of 2 kilograms of methane, which is CH4. Calculate the volume of 2 kilograms of CH4 that will calculate the volume of 2 kilograms of methane that will be occupied at STP. All right. Alright, so the first thing we gotta do is, because we're in grams here, this relationship works on moles. So we know that we're gonna need the molar mass. Alright, so we take our carbon and we multiply it by 4 hydrogens, and you end up with 16.05. So we take your 2 kilograms, and the relationship between kilograms and grams is that there's 1,000 grams in a kilogram. Kilograms go on bottom because we want to cancel them out. We then want to use that molar mass to go between the grams and the moles. So we're going to divide by 16.05. Remember, the number goes with the grams. 1 mole goes on top. And we're then going to use this new relationship of molar volume. So we say that that 1 mole is equal to 22.4 liters. The moles cancel out. We're left with liters. We multiply and divide, and we get an answer of 2791 liters. So 2,791 liters, which is a pretty considerable volume, but we also have 2 kilograms of a gas. So that sounds about right. So this is basically a new conversion that relates the amount of stuff in the mole, in terms of moles, to the volume. And again, this is only at STP. All right. Along the same lines of relating moles and volume and conversion to stuff like that, stoichiometry dealt with in the last video, or stoichiometry we talked about in the last video, dealt with the relationship between the reactants and products. And we can do this with a gas too. It basically follows the same line of thought as our mole-to-mole stuff. So, if you don't know what I'm talking about the mole-to-mole stoichiometry conversions. So you might want to refresh your memory on that from the previous video. Alright, so with the mole-to-mole stoichiometry, the coefficients in the Bell's equation can be used to describe the number of moles. Well, the same thing can be said for the volume. Okay, this actually should be moles. So coefficients can be used to describe the volume as well as the moles. Um, I do apologize about that. So, and we can use this to convert between the volume of one compound and the volume of another. Again, the setup is identical to mole-to-mole stoichiometry, except for in this case, we're using liters instead of moles. Our units change, but the same process and the same idea is true. So let's look at our example. What volume of oxygen gas is needed for the complete combustion of 4L combination? That should actually be combustion. I do apologize. Of 4 liters of C3H8, which I believe is propane. All right, so they give you the equation, and this is balanced. C3H8 plus 5O2 goes to 3CO2 plus 4 waters. I believe we looked at this before. We may have actually looked at this when we were talking about moles to moles. All right, so they give us 4 liters to start with. All right, that goes over 1. That's 4 liters of the C3H8. Okay, so we look at our balanced equation. We see that we have a 1 in front of it. So that's going to go on the bottom for liters again. And then we know that we want oxygen. So that's going to be 5. So that's going to go here. And then all we do is we multiply. So 4 times 5 is 20 liters of oxygen. Again, identical to the mole to mole. And I believe this might be the exact same example that we used with mole to mole. I'm not 100% sure, but you may look back to double check. So this is another way that you can, that's specific to gases, but uses the idea of stoichiometry. All right, so that finishes up the gas laws. The last topic that we have in this unit is energy. All right, I touched on energy briefly before talking about phase changes and whether it was endothermic or exothermic. And I'll get into that in a little bit, but just to go over the definitions real quick. Energy is really kind of hard to describe, but it's basically the ability to do work or to produce heat. Okay, the law of conservation of energy is the same as the law of conservation of mass or matter, that it can't be created or destroyed. It's just going to be transferring from one type to another. Heat is basically energy that's going to flow from something that is warmer to cooler. Now recall that there is no such thing as a cold object. There's no cold temperature. You have less heat in chemistry. So the flow is going to go for something from warmer to cooler. So if you touch something metal often in the morning, it's going to feel cooler to you because your body is warmer, has a higher temperature than that piece of metal. So the heat is going to leave your hand and move into the metal, and therefore you feel that cold touch. All right. Specific heat relates to heat, and this is basically how much energy is going to be required to raise the temperature of 1 gram of a substance by 1 degree Celsius. All right, these specifics are the detail here is it needs to be paid attention. It's to raise temperature by 1 gram of raise the temperature 1 degree Celsius of 1 gram of substance. And each substance has its own specific heat. Remember that we said that water's is 1.8, or excuse me, 4.187, I believe, degrees Celsius. No, that's incorrect. I apologize. I'm trying to do this off the top of my head. I know the value is 4.187. It's joules per degree Celsius grams. All right. I think that's the value. If not, double check your notes. Okay. That is a value that you do need to know. And the equation that relates specific heat to the mass and the temperature and all that is that Q, which is heat here, okay, is equal to the specific heat. Again, this is there's a particular one for each compound or each substance times the mass times the change in temperature. Now, remember that change equals final minus initial. Okay, so it's the final temperature minus the initial. You can have a negative heat, so it's not always the biggest minus the smallest. It's going to be the final temperature minus the initial temperature, what you start with. So let's look at an example. Alrighty, the temperature of a sample of iron with a mass of 10 grams changes from 50.4 to 25. with the release of 114 joules. What is the specific heat of iron? All right, so we know that our heat is 114, so that's going to be our Q. Our mass is 10. We don't know C, that's what we're looking for. And then our difference is 50.4 minus 25. All right, so what we do is we're going to divide the 114 by 10 times that difference, which is 25.4, and you end up with a specific heat of 0.45 joules per gram degree Celsius. You looked up in a table, this would be very close to what iron is. All right, so it's just using that formula previously to relate the heat to the specific heat to the mass and the temperature. All right. So again, let's talk about some more vocabulary, and let's go back to the phase changes. All right, so thermochemistry, we talked about briefly, was basically the study of heat exchange. Enthalpy, this is a fancy word for heat at constant pressure. So in your brain, you should say that enthalpy equals heat. So just when I say heat and enthalpy, same thing. Okay? And by the way, this is symbolized by an H. So if you get confused, H is enthalpy. If it's exothermic, H is negative. Okay, that means releasing heat. If it's endothermic, H, or the enthalpy, is positive. Important to know those. Alright? A thermochemical equation is basically going to show the amount of heat released or gained. Sorry, I forgot to mention this, but endothermic is when you gain heat, you put heat in. Alright, we have some enthalpies of phase changes. Okay, this is how much energy is going to be required to go from a liquid to a gas or whatever. Okay, now one thing I do want to stress, and that a lot of people had a hard time wrapping their brains around, when you're going through a phase change, the temperature doesn't change. The particles are moving faster. The heat that you input make the particles move faster. Let's see if I can draw a picture real quick. Because I feel like this is something that a lot of people were really, really confused on. Okay, so let's say we have a box. Okay, we got some particles. Let's say we have a liquid, because they're fairly close together. All right, let's put a flame. Let's assume that's my flame. Okay, I can't really draw, y'all. You'll know that. So we add some heat. What's going to happen is that this is not going to raise the temperature of the overall thing. Temperature is going to stay the same. So let's say the temperature is 100. Alright, so what's going to happen is this heat here is going to go into each of the particles. And what's going to happen here is that these particles are going to start moving faster. Okay, so they're going to start spreading out, they're going to start bouncing around a lot, and eventually you're going to get some that are going to leave this box or this bowl, and it's going to become a gas. Because so we start as a liquid, we're going to make a gas. It's supposed to be an L, a liquid. Let's try that again. It's supposed to be an L. Okay, that's an L. And so the heat doesn't change the temperature. The temperature over here is still 100. Once all these particles leave the box or leave the container, then the temperature will start to increase because we still have heat on this, and the heat is going to keep being added, but instead of going to the particles, it's going to go and it's going to increase the overall temperature. Okay, it's kind of weird to think about, but that's actually the situation. Okay, alright, so our heat of vaporization or enthalpy of vaporization, that's how much it requires to change 1 mole of a liquid to a gas. Heat of fusion, again, I have no clue why they call it fusion, just is. I'm sure one of y'all can Google that and tell me why. Is how much heat is required to melt 1 mole of solid, to go from solid to liquid. And what we can do is we can use these heat of vaporization or heat of fusion, and we can convert between the amount of heat needed and the amount of substance we have in terms of mole. So let's look at a quick example. Okay, calculate the heat required to melt 25.7 grams of methanol, which is C3OH, at its melting temperature. The heat of fusion for methanol is 3.22 kilojoules per mole. All right, so the first thing is if you notice, this is moles and kilojoules. So that's our conversion there. So they give us grams, so we gotta find the molar mass. We gotta convert our mass to moles. Alright, so we have 1 carbon, we have 4 hydrogens if you count that on the end, and we have an oxygen. And that gives us a total here of about 32 grams, 32.05. So take our 25.7 grams, we're going to divide by the grams, because we want to get rid of the grams. That's equal to 1 mole, and then we use that conversion for the heat of fusion, which is 1 mole on bottom and kilojoules on top. So again, it's 3.22 kilojoules for 1 mole. You can also do this in multiple steps, so you can find the number of moles first and then multiply it by the heat of fusion, but I just kind of do it in one because it's easier. So we multiply, we divide, and we find that for this particular amount of methanol, you need 2.58 kilojoules. Again, we're using this heat of fusion as a conversion between the moles and the energy, or the heat. Alright, I know that's a lot of random topics. They all kind of connect. There's a good bit of math in here. This is probably this is our heaviest unit on formulas and stuff. But this concludes the video on Unit 8. The next one will cover the most recent unit we covered, which is a hodgepodge of different topics at the end of the year.